Hello, welcome to my tutorial on indexing in R. If we haven't met before, my name is Colin Edwards and I'm a theoretical ecologist, currently working as a postdoc at Tufts University. Most of my work involves programming in R, and I really enjoy mentoring and running workshops on the fundamentals of programming. Today I want to try something a little bit different. I'm going to present a workshop in video form. This workshop is on indexing, which is an incredibly powerful tool that most R users will need to use to select parts of their data or other objects. This workshop stems from working with biologists to improve their R proficiency, and I'm assuming that you have R and RStudio installed, but I'm not going to assume much more in the way of a background. A little bit of housekeeping. This is my first time doing this, and I want to try to keep it fairly intelligible. If you are familiar with the basics of R, the first parts will probably be a little bit boring. So I'm going to have a running header up at the top that I'll try to keep updated so that it's easier for you to skip ahead to stuff that you might not be familiar with. We're using R, we're using RStudio. If you're not familiar with RStudio, we kind of have a section off over in here where we can write in scripts. And then over here, those scripts are actually going to be essentially run in the program itself, and we can type directly into the console, but that doesn't leave us a record of what we're doing, so I will mostly be working over in here. Down off to the bottom left, we have information about our environment, history, and connection. This is not a section that I usually use very much. Bottom right, we have plots, packages, etc. I will mostly be ignoring that section as well. If you are just opening up RStudio, you may have these panels arranged a little bit differently. It is relatively easy to switch the orientation of the panes. I like to have the console on the right so that my script and my console are not fighting for vertical space. The other thing that is probably worth telling you now is that there's kind of two ways that you can do very simple things in R. So if I wanted to make an object called rat and I wanted to give it a value of 10, I tend to use an equal sign. And you will also see other people use that. And in fact, actually, nerd alert, digression. So the origin of this arrow, which for us is two keys, actually comes from, I believe, one of the precursors of R. And at that time, there was a single key on the keyboard that made that symbol. And so it was, not really time wasting to try to type those two things. I am lazy. These two things are effectively interchangeable. If I run either line, we get the same results. Oh, you know what? Actually, I'm going to pause real quick. And I'm going to increase the size of all of the text here. Actually, I realized maybe I should show how that's done. Let's see. So we are in So tools, global options. Over in here, we've got an appearance section. I can zoom things in, but maybe I will just set that to like 16. The goal is that you are actually able to read what I'm doing. All right, so these two lines are effectively interchangeable. There's a sort of an edge case where they're not, so you can actually use this as part of an argument for another function that's pretty specific. Otherwise, it doesn't matter which one you're using. And I will be using this one, but if you prefer the arrow key, you are more than welcome to use that instead, and you can just imagine that every time I write a single equal sign, it's actually a less than and a minus sign. All right, cool. So I think that's enough with the nerd alert. Let's get into the basics. All right, so our building blocks in R are called primitive types, but I like to think of them as atoms. So when we make a variable, like for example, let's make the variable animal. We can make it equal to a number, which is numeric. So if we said class animal, we would see, hey, it's a numeric. We could also make it equal to a character string. So like animal equals turtle. And now class animal gives us character, short for character string. There's another type that we're going to deal with later in this workshop, which is a Boolean, which is true or false. So animal now is equal to true, and if we go class animal, we see it's a logical Boolean, either way. And so that is the basic building block that we're working with. And if we imagine, let me pull up a whiteboard here. So if we imagine that our code says something like animal equals 10. So what's actually happening is that we're telling R, hey, make a single box and put the value 10 in there. And when we say animal equals cat, we're saying make a single box and put the character string cat in there. And this is really simple to deal with, because then if we tell R, hey, grab animal for us, well, obviously we mean whatever is in animal. Might be 10, might be cat. This gets a little bit more complicated when we step into vectors, which we're going to do right now. All right, so let's get into vectors. Vectors are I know I said that atoms or primitive objects are the building blocks of R, but vectors are really the building blocks of a lot of science. So the idea with a vector is that instead of having one thing, actually let's go back to our whiteboard. So if we were to instead want to store like 10 things, well, no, 10 things is way too complicated. If we were to instead want to store, say, 3 different types of animals. Oh wow, that's big. With a vector, we're actually saying, hey R, make 4 different things, and each of those things might hold a name. Like maybe this is a cat, and this is a turtle, and I think probably we need a unicorn in here, and then a rat. So the way that we make a vector in R, if we go back over here, is using the C, which is short for concatenate. So that's a function. If we say, let's see, so we wanted cat, turtle, unicorn, rat. So cat, we can actually give it multiple arguments. Turtle, unicorn, rat. So the C function says, hey R, take these different building blocks and put them into a single ordered sequence. So here we can see cat, turtle, unicorn, rat. We need to actually save that into a variable name or an object so that we have something to work with. So now if we look at what is in animal, we see that. So you'll notice I had some really awkward wording there, right? An ordered sequence of stuff. It's very natural to want to call this a list. Lists are actually a separate type of data in R, and so I have to avoid that term. So now animal gives us all 4 of those things, which means that we have to do something to tell R when we actually just want, say, the second part. So the way that we tell R we want the second item in that box is using what's called indexing. And the nomenclature for that, the syntax, is square brackets. So square brackets is just telling R, hey, we know there's multiple boxes in this, and we're trying to identify which ones we want. And there are, 3 main ways that we're going to talk about indexing. So the first one, which is really easy, is that we can think about these as they're ordered, so they have numbers. If you come from another programming language, you're probably used to the first box being numbered 0. R was designed so that the first box is numbered 1. So if we wanted the second box, we can actually just type a 2 in there. And now, if I run that line, oh, I forgot to mention, you can copy a line, Control-C, and then paste it, Control-V over here. There is also a hotkey, so Control-Enter, I think Command-Enter on a Mac, will automatically run that one line. So when you see the stuff rapidly appearing from over here to over in the console, that's what's happening. So if I run that, like I said, we get turtle. Cool. So that was the second object that we had. Oh, you know what I forgot to do? We are now talking about, yeah, there we go. So, okay, so that's the second object that we're working with, the second item on that list of boxes, not list, that ordered sequence of boxes. The cool thing is we don't have to give it a single number. So if we wanted both turtle and rat, we can actually make a vector of 2, 4, and if we run that in here, C of 2, 4, R says, you're identifying 2 boxes, numbers 2 and 4, turtle and rat. If you want to write this clearly, you can actually, well, actually, even without the vector. So if we think about a 2 here, that doesn't have to be a 2. It could instead be a variable with a number stored inside of it. So if we said index equals 2, animal index, R says, what lives inside of index? Oh, that's a 2. Okay, so we're supposed to grab the second box. Similarly, we can make this into a vector. And bam, animal, we're grabbing boxes 2 and 4. This process of storing the vector and then putting it inside of a box is somewhat handy if you're going to be doing complicated things. And I also find if you're doing something really weird in terms of defining the list, it can be really awkward to have something very long inside of the square brackets here. So this is probably a good time to talk about a sort of separate function in R, which is very handy, which is if you want to make a vector, which is every whole number from one number to another, like say if you wanted every whole number from 2 to 10, you could do that by going 2, 3, 4, 5, 6, 7. Oh my God, this is so hard. 8, 9, 10, and that does what we want. But that was also time consuming, and you could imagine that if you actually wanted, a vector that went from 2 to 100, that just gets really gross. There is a very simple function in R which is using the colon, and that generates the same thing. So you give it the first number and the last number, and it automatically fills in with every whole number in between. This is somewhat useful in general, but incredibly useful for indexing. So here, if we wanted items 2, 3, and 4, we can just do 2 through 4. Bam. The other one, again, this is a little bit of an aside, but this doesn't have to be a number. Again, it can be a variable or the result of a function call. And so I will often be dealing with a situation where I need to grab from some number, say 3 or 4 or 2, to the end of a vector. And right now we know that this vector has 4 items in it, and so 2 through 4 works. But if you go length animal, that tells us 4. If we made animal a lot longer, this would always give us the number of boxes in animal. And so we could actually go 2 through length animal, and now it behaves exactly the same right now. But if at some point in the code I changed this so that animal was actually a vector of 1,000 entries, it would go 2 through all of them. Cool. Okay, so that is the use of colon. That is identifying the boxes that we want. If we go back here, so let's do a little bit of erasing. So imagine that instead of identifying the box that we wanted, we knew that we wanted to not have the first one. Well, we could, one option is to say, okay, we want boxes 2, 3, and 4. So we can say C of 2, 3, and 4. Or if we're clever, we can instead say 2 through 4. And in fact, there's actually a function tail that, anyway, we don't have to get into tail, but tail kind of does the same thing. But there's this other way of identifying the boxes that R should return to us, which is to identify the boxes we don't want. And we do that with negative numbers. So animal -1 isn't actually saying grab the -1th box, because there isn't one. And instead, it tells R, hey, grab everything except for 1. which is the same as grabbing items 2, 3, and 4. Just like identify sort of this positive identification, we can give vectors. So we can say, well, we don't want items 1 and 4, but we want items 2 and 3, which here should give us turtle and unicorn. Wow, I misspelled unicorn. Interesting. And it works. So we see that we get turtle and unicorn. I believe we can even -1, 4 to -1. So you can even use negative numbers with colons. So if you knew that you wanted not, say, -2 through -4, if you wanted everything, well, in this case, if you wanted entry 1, you could do this. That's a really complicated way of doing things. So we can identify the numbers of the items that we want, and we can identify the numbers of the items that we don't want. So the third way, I should maybe label these. Identify what we don't want. Identify what we do want. For completeness, we can obviously also do something like index equals -1, animal index, and we should get items 2, 3, and 4. Oh, whoops. I need to run line index equals -1, and now we get items 2, 3, and 4, so everything except for cat. So the other thing we can use, I'm going to call them booleans. I think R sometimes calls them logical primitive types. But we can give a vector of trues and falses. And this is the least intuitive and most useful tool that we have. So let's do some erasing again. So we're going to make these by hand at first, and then we're going to get into why they are so useful in a little bit. So if I wanted cat, and well, actually, let's just start with if I wanted cat. What I could actually do is make a vector that's a true and a false and a false and a false. And if I give that to R, inside of the brackets, R will return only the items in the boxes that correspond to trues. So if I went over here and I said, here's where I really like to make a separate variable to store this, because it gets kind of messy. So if I said true, false, false, false. This is another case where people can code these differently. So if you use, you can use uppercase T and uppercase F instead of true and false. It's faster to type. In this case, I really like writing it out. I find that it's a little bit harder for me to misread things, but you should do whatever makes you happy. All right, so that's our index. And if we look at it, we can see, yep, true, false, false, false. And so now if we take our vector, animal, and we index in, we essentially, oops, true. We essentially feed it that index in the brackets, we get cat back. And so that's what we should get. The first item is cat. Just like before, we can identify multiple things by replacing one of our falses here with a true. Nope. Replacing one of our falses here with a true. And so in this case, we're saying, hey, we want items 1 and 2, or 1 and 3. And so if we took this, ran that line again, so now index has 2 trues, and we get items 1 and 3. Fantastic. All right, so let's take a minute to talk about why we might actually care about booleans, because man, this is a lot more annoying to type than just saying, hey, grab -1 or grab 2 and 4. Okay, so the real value of booleans is the fact that we can write tests in R that give us booleans back. So the simplest tests are ones involving math functions. So let's make a vector which I will call vec, And we're just going to make 1 through 10. So if I look at vector or vec, we see 1 through 10. All right, so one of the simplest things to do is just say, hey, greater than 5. And so what this is telling R to do is, hey, look at every item in vector, give us a true if the value is greater than 5, give us a false if it is not greater than 5. So if I run that, we see false, 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 true, 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 true. That makes sense. So these ones should return false, these ones should return true. And what that means, since that is a vector of trues and falses, we could save it somewhere. Like we can make this object called ind, and now we can index into vector using those trues and falses and grab everything that is true. So this is a really long way of saying, hey, if I wanted to grab all of the entries in vec that were bigger than 5, I can do it using this. Now there are a lot of there are a lot of familiar tests in R. Greater than and less than are obviously very easy because we have an actual key for that. If we wanted greater than and equal to, let's put this, let's put this on here. So if we want greater than, that's easy, right? We just do that, and similarly, less than is that. Greater than or equal to is two separate symbols, so we just use the greater than sign and then the equal. Ditto for less than and equal. We'd run into this problem of what if is equal? How do we test that? Equal. I can spell. Well, we can't use an equal sign because we use that to create variables. And so instead we use two equal signs. So if we look back at R, if we wanted to say which values in vec are equal to 5, we can use the double equal sign, and we see that there's a single true, which corresponds to the fifth item. And if we grab only those values that are equal to 5, hey, we got it. Similarly, less than and equal to 5 should grab us, we should have trues for the first 5 items. 1, 2, 3, 4, 5. Fantastic. There are a few other useful functions. So if we look at vec for a sec, we can, let's combine 1 through 10, but also let's add an NA on the end. So if we look at that, we have an NA. There is a function in R called is.NA, and it gives us a true if it is an NA. And so if we said, hey, ind equals is.NA, so now our ind object is the true falses with that true in the end, and we could grab just our NA objects. That's frankly not super exciting there. But this is actually a nice example of when we might want to use the exclamation mark. So true is true. But if we use exclamation mark, that reverses trues and false. And so if we look at ind, we have a true for our 11th item, because that is an NA. But that also means that not ind, where that means not, gives us all trues except for where there's an NA. And we can actually use that for our indexing. So this is something that you might use a lot if you have data with some NAs and you want to do some analysis that doesn't allow NAs, so you have to remove all of the entries that have NA in them. This sort of function. Again, I for something like this, I like to save it as a separate index object, but you can also absolutely do exclamation mark is.na vec. That's a little bit longer to read in there, but that does the same thing. If we are dealing with characters, well, actually, no. In general, if we have, how do I put this? Oftentimes, I will be working where I have some list of maybe experiments or maybe sites that I'm particularly interested in, and I want to grab all of my data that's from those sites. So we might have something like sites.cool, which might be temperature, or it might just be these are the cool sites that I want to see, are sites A, B, and D. And then I might also just have data, sites.data, and maybe that's going to be, I don't know, it might be not ordered, so we might have a C, and then an A, and then an A, and then a C, and then a D. So what I really want to know is, hey, I want to grab the entries in here that are also in here. So I want something that is 5 long, and I want it to be, C should not be in there. Oh. But A's and D's should. So I want something that says false, true, true, false, true. All right, so let's try coding that up. So over here, we have our sites.cool equals C of A, B, D, and then we have sites.dat equals, we can make that slightly more readable, CAACD, cool. C of C, A, C, D. Cool. So if I say sites.dat equals sites.cool, R gets really upset because this is not the same length as this. And what R really wants to do is to test one at a time. So the first against the first, the second against the second, the third against the third, the fourth against the fourth. Oh shit, there's no fourth. Or R wants to have a single thing, say equals C, and then R can just test C against C, C against A, C against A, C against A, or C against D. So if I run that, it's fine, and it gives us the entries that are C. But the equals sign, or the is.equal function, does not handle two different vectors of different lengths. But there's this other cool thing that uses really weird syntax, percentile in percentile. So this is saying which of these items here also live in here. Let's give ourselves a little bit more space. So if we run that, we get false, true, true, false, true. And in fact, if we say, hey, we want to index into that, or index into sites.dat using that, we get AAD. Excellent. Now we might actually, see, this is where it starts to look a little bit complicated, and so maybe we create a separate line that identifies the sites of interest, and then we can use the brackets to grab them. Cool. The other thing that is worth noting is that int right now is trues and falses, and it will often happen that we really want to know what is the entry number for the trues. So ideally we want something that says 2, 3, and 5. And there's a function in R called which. And that just says which of these trues and falses are true. 2, 3, and 5. It's worth noting that if we run which on our ind and index in, we're just switching between giving trues and falses to grab the boxes that we want and giving the numbers of the boxes to grab the boxes that we want. We get the same results either way. Okay, so far I've been giving us kind of inane examples to work with, very, very simple things, because I think that is useful for trying to figure things out. But I want to walk through some of the powerful aspects of indexing, and to do that we need to think about having an actual data set. So let me talk real quick about a type of experiment that I've run a few times. The basic idea is we have some plant, and I want to know if the plant defense traits end up impacting how well herbivores perform on it, how well herbivores grow, and how well the plant manages to kill the herbivores. So we've got some little bug. This looks like a spider, but we're going to put on 6 legs, so is that 6? That's 6. So it's going to be an aphid. I've done a little bit of work with aphids, but more with monarch butterflies and swamp milkweed beetles. So we do something where, like, on day 0, we put a bug on the plant. And then one of two things happens. Either the bug gets a lot bigger. So I come back on day 7, and I see, hey, did the bug get bigger? Or did the bug die? And I also measure some plant traits over here. What does plant look like? So we end up with 2 measures. We have survival, and we have weight. And then on the plant, there's a few things that we might measure. I think maybe for today we'll just think about trichomes. So many plants, I was working with milkweed, common milkweed, Asclepias syriaca, for my dissertation, but many plants actually have a bunch of little hairs on them, and they make it difficult for insects to get at the delicious, delicious leaf tissue. So we might measure the plant trichomes, and we might be curious, are the plant trichomes affecting how well the herbivores did? Whether they grew a lot or a little, and whether or not they survived. So when we measure these, we're going to end up with a few rows. So we have something like plant ID, or a few columns. And we have something like trichomes, which I tend to abbreviate as trich. And so this is just literally counting the number of hairs on the leaf, or some small part of the leaf. And then we have weight. And typically when people do this, they often will put a 0 where the insect died. And that doesn't mean that the insect actually weighed 0. It means that the insect died and was never weighed. And so we're going to have multiple rows. For now, for this example, I want to treat these as 3 different vectors. So let's go into R real quick. And we will make up some data from an experiment. Make up experiment data. So we're going to have a vector called ID, and I'm just going to call that, I'm just going to have it be letters, and we're going to have 5 different plants, A, B, C, D, and E. And then we will have trichomes. That will be another vector. This is going to be actual numbers, made up numbers, but maybe the first plant we had 117 hairs, and the second plant we had 200, and the third plant had almost no hairs. There is actually a huge amount of variation in milkweed plants, but this isn't a biology lesson. This is about programming. 214, and maybe like 150. And then let's put in some weights. And we are going to have, so we'll have these be in milligrams, but it doesn't really matter. So we'll have something like 220, and then this one, man, this guy got huge, and then this guy died, and then this guy, actually this guy was enormous, or there was a measurement error, and then that guy died as well. Okay, so if I run these, what all might we want to do? Well, if we were to plot weights, we can see, hey man, there's one that's over 1,000. That's huge. We could use indexing to to figure out what the actual weight there was. Bear in mind, this is 5 entries, but you're probably working with data that has more than that. Maybe you have several hundred. And so figuring out exactly the value of that one matters. All right, so if we said, what would be a good test for that? We could say ind is equal. So I tend to write ind when I'm thinking about indexes, but you can call your vector of trues and falses whatever you want. So ind is equal to weights greater than, well, we know that there's only one that's greater than 1,000. Okay, cool. So ind is giving us 3 falses, true, false. We could grab the weights. Using index, we can index in and grab only the entries that are more than 1,000, and we see that the entry that's a problem is 1,500. But we don't necessarily care what the weight is. What we might care about is, hey, which plant was that? Do I remember that that plant was weird? Or is that a plant that I wasn't expecting to be weird? So the really cool thing is, what is ind? Ind is a bunch of trues and falses. Now we got those trues and falses by running a test on weights. But ind isn't keeping track of the fact that it's weights. It's just 5 trues and falses. Which means we could actually index into another vector of length 5, like say IDs, using that same set of indices. And so if we do that, then we're grabbing the plant number for that wonky entry. So we had a really high weight on the insect, and that was the plant D. Similarly, we might be wondering if, like, oh, maybe that entry or that plant had super small levels of trichomes. So what's the trichome count for that? So this is incredibly powerful, this ability to run a test on one piece of data and then look at the corresponding pieces of data. There's another thing which I haven't talked about yet, but is also incredibly powerful, which is that you can use indexing not just to look at entries, but to change them. So I am working with a collaborator. In my data, I put NAs wherever the bug died. In his data, he put zeros. And so to make it all consistent, I wanted to change those zeros to NAs. So if we said weights equals 0, we get trues where the bug died, right? Remember, those zeros aren't real zeros. They're fake zeros. All right, so we might store that somewhere. And if we grab the entries in weights where ind is true, we see, yep, they're zeros. But we don't just have to view that. We can actually then assign values to it. So in this case, we want it to be NAs. But this is a tool that you might use all over the place. So now if we look at weights, our entries that had 0 have NA. Similarly, remember that is.NA of weights should give us trues and where there is an NA. So if instead of changing my collaborator's data to look like mine, we wanted to change my data to look like my collaborator's, again, this is just exactly the same process, equals 0. Bam. Cool. So there's another thing that is useful to mention when it comes to tests. Sometimes you want to chain things together. So sometimes you want to know, for example, what are all the entries that are less than, well, yeah, let's think about trichomes. So if we wanted to know, hey, what are some of the extreme trichome values? What are the trichome values that are less than 100 or greater than 200? Which, if we eyeball it for our 5 values, we can see that we should have a 24 and a 214. So trich greater than 100, or less than 100, is giving us a true on the 3rd item, which is our 24. And trich greater than 200 is giving us a true for our 4th item, which is our 214. So if we want to chain several tests together to sort of enact them simultaneously, we can do that using either an and sign if we want both of them to be true, or an or sign if we want either of them to be true. So trichomes less than 100 or trichomes greater than 200 gives us trues for entry 3 and for entry 4. And if we store that in our indices, and then we grab trich of ind, oh look, those are our more extreme trichome values. And again, like I said before, we don't have to index into trichome. We can index into anything of the same length. So maybe what we're really interested in are what are the plants with the most extreme values of trichomes. Oh, plant C and D. And then maybe I go back to my field notebook and I notice that like C was in a really dry place and D was in a really wet place. Actually, probably the other way around. But again, that's the biology side of things. But this is a powerful tool for digging through your data. The and sign is basically, it gives you a true if both of them are true. So in this case, ind will be all falses because there's no way that you can be less than 100 and greater than 200. But you could chain together several things. The cool thing, again, is that this and sign doesn't care whether it's the same source of tests on either side. It just cares that we have 5 trues or falses here and 5 trues or falses here. And so we could do something like, I want all of the entries where trichomes are greater than 100 and weights, let's see, what do we have in weights right now? So zeros are dead insects. So maybe I'm interested in where are the plants where there were a lot of trichomes and the bug died. So the bug died for weights equals 0. Trichomes greater than 100 is saying there were a lot of them. Oh, that final plant is the one that had a lot of trichomes and killed the insect, plant E. Cool, so that's ors and ands. And I think that really covers everything that I wanted to talk about on vectors. So I think it's time to add another dimension. So actually, I lied. There's one more thing that I should mention about vectors, and it really comes up when we're talking about two-dimensional objects. A vector, right, we make it using the C, it has to have all the same type of object in it. So 1, 2, and 3 is fine, but if I actually said 1, cow, and 3, R says these all have to be the same type of thing. And so it's actually going to coerce 3 and 1 into being character strings because there's no way that you can get a number out of cow, but you can turn a 3 into the character 3. That's probably not going to come up too much when you're dealing with vectors, but I want to briefly talk about matrices. And so let's see, matrices. Matrix? We'll just call it matrix. So let's comment out kind of a block section here just so that it's easier to separate what we're doing. So a matrix is, well, no, let's go back to the drawing board quite literally. Here we are. So a matrix is, rather than our collection of boxes like this, a matrix has multiple dimensions. So we might have something, I tend to call my example matrices Matt, and so we might be saying, hey, Matt is going to be a bunch of entries. I'll probably just put in animals because they're easy to remember. So if we wanted this to have 3 columns and 2 rows, we can do that with Matt, or whatever we wanted to call our variable name, is equal to a matrix. So the simplest way to make a matrix is to fill it in with a single type of character or value. So this is what's going to go in the matrix, and row equals 2 and call equals 3. So if I did that and then I ran Matt, we can see it's all zeros. So what I might actually want to do is give it a vector of entries to fill in with. So maybe we've got our cow and a rat and obviously a unicorn. And then I'm thinking maybe a cat and a turtle, and this really could use a dragon. So let's see. I can hit enter anytime after a comma, and R will know to keep running on to the next line. when it's running that line. And so now Matt should have characters in it. So one of the heads up things is that I tend to think about matrices as being filled left to right because we read left to right. R wants to fill them column wise first. So I tend to think that it should be cow, rat, unicorn across the first row. And R instead thinks, oh, cow and rat should be in the first column. You can change this default behavior by saying, actually, I always forget the syntax for this. By row. There we go. So we can say by row equals true. That's just an additional argument. And now it fills it in the way that I think it should. Cool. So now my brain is actually matching what's in our matrix. So everything that we talked about for vectors works for matrices, except that now instead of saying we want the if we wanted this entry here, which just to make sure it matches up is turtle. If we wanted turtle, we can't just say, well, we want item 2 or item 2. We need to tell it both the column and the row that we want. And conveniently, it actually shows us the syntax. But essentially, we're going to give it the row name and then the column name separated by a comma. So that entry is the second column and the second row. So we're going to do something that looks like row, comma, column, which in this case is 2, 2. And if we wanted this one so that they're not symmetrical, that's the second row, so 2, and the third column, 3. And lo and behold, that works. So 2, 2 should give us turtle. It does. And second row, third column should give us dragon. And it does. Fantastic. Just like before, we can grab multiple entries at once. So if we wanted the second row and the third and fourth column, instead of putting a 3 in there, we can use a vector, so 2, 3, and that gives us turtle and dragon. Now, there's this other complication, which is oftentimes we want all rows or all columns. So for example, maybe I want all of the values in the first row. So like, how do I identify this thing here? Well, I want the first row, so that's easy. And then what do I put over here? Not actually a question mark. What happens is we leave it blank, and R interprets that as everything. So if we say mat 1, comma, that will grab the first row, all of the columns. And that is, in fact, our first row. Similarly, we can combine this with other things. So we might, for example, want the first and second row, all columns, which in this case should be the entire matrix. And that works. And just like before, if we wanted to skip the first column and grab all the rows, if we're doing all the rows, we leave that section blank there. If we want to skip the first column, we can use a minus sign there. Oh, look, that did it. And, just the same as before, we can use multiple negative numbers. We can also give trues and falses. So if we wanted true, false, false, that gives us the first. Is that doing what I want? Cow and cat. Yeah, all rows for the first column, cow, cat. Cool. And just like before, we can do something like a test. So like int equals mat equals cow. And then mat int should give us all of our cow entries. The way that works actually is that we create a matrix of trues and falses rather than a vector. But it's the same principle. So sort of all of our indexing tools work here. There is one additional set of tools for indexing that's worth mentioning. So our matrix right now has no column names. But maybe we want to name those columns. Maybe we're going to name them, I don't know. What do we call it? Day 1, day 2, and final test. So maybe we went back to each site multiple times and looked at what animal was there. And so now, if we look at map, we can see that there is a name for each of these columns. If you were to read in a data file, you would often have the first row be headers, which would become the names for your matrix. What you probably have is not actually a matrix, but a data frame. We're going to get to those in a sec. But I want to point out a useful tool here, which is if I know that I want everything in the date 2 column, or maybe the final test column, rather than figuring out, okay, wait, it's the 3rd column, so I can put a 3 here, unicorn dragon, fantastic. I could instead just give it the name of the column as a character string. That does the same thing. And just like identifying using the column numbers, I can give it multiple things as a vector. So maybe I want date 1, and final test. Boop. There we go. And that grabs them. Excellent. Cool. There's one other thing which I realized that I could have mentioned before, but I will mention now. You don't have to give the numbers sequentially. So imagine that what I really wanted is to take the matrix that I have, but flip rows 1 and 2. So essentially what I have right now is that, but I could say first I want row 2 and then I want row 1. And if I run that, we've switched the 2 sides. And in fact, if I wanted to, this could be the same entry multiple times. So if I wanted to take that first row and make like 6 copies of it, I can do that. This is something that I use a lot less in analyses. It's a little bit more useful for some simulation situations. But I thought I should mention it because we're talking about indexing. Excellent. So now, enough about matrices because the one last thing on matrices is just like vectors, a matrix has to be all the same character type. So if I was to give the matrix, what am I doing? I can copy paste. So if I was to, instead of cow, if this was to say 10, just the number 10, R is going to say, our matrix has to have all the same data type. I have to turn that 10 into the character 10, because obviously I can't turn rat, unicorn, cat, turtle, or dragon into a number. And so now if I look at mat, we can see that it's been coerced. That's the technical term. It's been coerced into a character string. But oftentimes, we're working with data where we want it to not all be the same type. For example, we had our data from my hypothetical experiment. This is a character string. This is not. This is a numeric, and this is a numeric. So what I really want is what's called a data frame. So data frames are where this all becomes super powerful. So oftentimes you will make a data frame by reading in your actual data sheets. Whoops. Let's create a different section here. I want to make one that we're familiar with rather than read in a CSV that you might or might not know. So let's see. So remember that we had ID, weights, and trichomes, which I was calling trike, from our hypothetical experiment. So we can make a data.frame with ID equals a vector of things, in this case, the vector called ID. Weights is a vector of things, again, in this case, that. And trichomes is a vector of values for trichomes. So to be clear on these, I am reusing code that I already wrote, which says that trichome exists and it's those values. I could actually do this with commas in there. This is essentially what we're actually telling R, right? Is that make it a vector 117, 200, 24, 214, 150. In these cases, and in this case, that vector already existed, and so rather than retype it, I can just call it. But if I run this, we create what looks like a matrix, but the first column is all character strings and the others are numerics. So let's save that. I'm going to call it dat, because that's what I tend to call my data, dat. And so again, I can just look at dat. It has column names, ID, weights, and trike. It has row numbers, but we're not going to work with those too much. If you're not familiar with RStudio, there is a super useful function called view, which essentially pulls up almost like a little spreadsheet in R that lets you look at your data. You can also do things like sort by and so forth, but I try to do that in my R scripts rather than clicking on the interface here. Cool. So this is really what our data is probably going to look like. We're probably going to have some columns that might be character strings that correspond to dates or to a site or whatever, and then we'll have some values that we're interested in. Or maybe our response variable is actually a character string. Maybe it's we've got some sort of qualitative measure of did the plant grow into the big category or the small category, whatever. So just like before, we can do things like say, oh, well, actually, no, not like before. So I was identifying how we can grab specific columns with matrices, right? So if this was a matrix and we knew we wanted the weights column, we could look over here and say, weights is the second column. So we want all of the rows and the second column. Bam. Okay, cool. That's our weights. Or we can be fancy and we could name it and we get the same thing. Both of those totally work, but they're kind of a pain to write. So because this is a data frame, which means it's technically a special type of list, we can use the $sign to grab specific columns, and then we just type in the name of that column. And here you'll notice there's no quote marks. If we do this, I believe, oh, it does work. Oh, that's fantastic. Okay. But we don't have to type in those quote marks. And so we can just literally grab specific columns. So this makes it really easy to, for example, if we wanted to plot something, we can say plot trichomes on the x-axis, x equals trichomes, y equals data, bam. And this is rather than doing something fiddly, right? We could also do something like, where did we go? Here we are. So we could do something like grab the third column and the second column. This is technically identical, but it's a heck of a lot harder to read and understand. Also, it doesn't automatically label the axes with anything meaningful. Cool. So remember before how we were interested in the entries where the insects died, right? So before we did something like dat $weights equals weights equals 0, and we see false, false, true, false, true. Because this is all one big structure, now we could grab all of the columns for those rows. So we could say, hey, let's grab the rows where the weights are 0, and let's grab all of the columns. And so here we can now get a much better look at what is happening with our data. And in fact, maybe we're running two analyses, and one of them we need only the entries where the insects died, and another we need only the entries where the insect lived. So we might say dat.dead equals dat of end, and then we could do something like dat.lived equals dat of not int. So this ability now to index rows based on conditions for specific columns is fantastically powerful. It allows us to identify outliers and figure out what's going on there. It lets you subset your data to make plots. It's incredibly potent. And I don't know that I really have anything more to add right now. Hopefully you found this useful. I'm still figuring out how to run these workshops through YouTube. So if you have any suggestions, let me know. And yeah, hopefully I'll talk to you again soon.